Alright, so we're going to start with A, and then A says solid via blah 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 blah. So we're showing that the speed is given by that. So we're going to start with the formula for the conservation of energy, where we say mechanical energy. Initial mechanical energy should be equal to final mechanical energy. So you can put there initial, and then there you can put final. So to start off with this initial and final, so the mechanical energy is simply potential energy U, and then plus kinetic energy K, so which is potential energy U plus kinetic energy K. Now the potential energy comes down as potential energy, but the kinetic energy can be split into rotational and let's see, can be split into rotational, and then it can also be split into translational. I mean, same this side, so U plus R and then plus K. All right, so analyzing the situation, at the top of an incline, you have the ball is not moving, so you have no kinetic energy. So both of these two things cancel out. So these two things are going to cancel out because the ball is not moving, so it doesn't have kinetic energy. So neither rotational nor translational kinetic energy. So those two cancel out. So here you're just going to win with potential energy, which is just U being equal to this side. Once the ball reaches at the bottom, it doesn't have any potential energy, but it has both the rotational and the translational. It has both the rotational and the translational energy. All right, so we're going to continue by saying this. The potential energy is given by mgh. The rotational energy is given by what? 1 over 2. And then we have the inertia, angular velocity squared, and then plus the translational is just 1 over 2, and then mv squared, like that. All right, so plugging in here, we can replace what? The inertia and the angular. So we can say our mgh is equal to, so we're going to have the same 1 over 2. So inertia of this solid sphere is going to be given by something else, which is what? Which is the 2 over 5, and then mv squared. So that's just for the inertia part. And the angular velocity part, we're going to have we're going to change this angular velocity into the linear type of velocity. So this is going to be v over r, and then it's going to be squared, since it's squared, because usually it's supposed to be v is equals to w r. Oh, sorry, that's not w, rho r. So making w the subject is over r. So that's how you have this one is equals to this over this. Yeah. But so we have that, and the last one that we're going to write is just the same one, plus 1 over 2. Let me just write it down here. All right, so it's going to be plus 1 over 2 mv squared. So what you're going to notice is that you're going to have some things that are similar. All right, so like for example, m is common in each of them. So m there, m there, m there, it goes. What else looks common? I think that's it. That's common. 2 here and 2 here goes. What else is common? The r here and the r here squared, since this squared is going to be distributed to both of them, so they go. So you're going to mean with what? We're going to mean with g h being equal to 1 over 5. 1 over 5, and then v squared, and then plus 1 over 2 v squared. All right, so at this point we're going to have a comma gh is equal to, if you add 1 over 5 plus 1 over 2, it's supposed to give you a 7 over 10, and you're going to have v squared like that. So cross multiply, this is going to be 10 gh is equals to 7 v squared, 7 v squared, so over 7 on both sides. Then you should have something that says v squared is equals to 10 gh over 7 root. We're going to have root of 10 gh over 7. So this is our expression for the velocity. So I think we're done with the first part. So we can go to the second part that says the acceleration of this guy here. So finding the acceleration,